Thank you so much, and thanks so much for the invitation to come here and speak at this wonderful conference and this wonderful program. I'm just going to get it off my chest. I'm a little nervous to talk to you all because this is the most physicists I've ever spoken in front of. But at the same time, I really think these communities have been just unbelievably welcoming. And so I really thank you for that. It's been really great. And so I love coming in and trying to learn all this new stuff and maybe contribute a little bit, but certainly it informs everything that I've been thinking about. So I don't have a picture of the three overlapping circles, but this talk is going to be mostly, again, in the intersection of condensed matter and mathematics. And at some point, we might do a little phase transition into math, into some intense mathematics slides, because people keep on asking me about types of Neumann algebras, so I felt like I had to say something about that. But I've marked where that happens, and it's called Intense Math Slide 1 out of whatever. And if you can get through those, you can come up after the talk and you can get your certificate for Intense Math Learner. Okay. Forward. Okay, what's our motivation? So given a 2 plus 1D lattice model, so all the lattice models that we study, if you have one in your hand, you know how to calculate what the topological order is. But I'm a mathematician, and what I want is a model-independent way to extract the topological order. Just no matter what you give me, I do the same thing, out pops the topological order. Okay? Just a machine that you put in. So here's my strategy for how we do this. This is joint with, on the last slide, joint with Corey Jones, Peter Nikens, and Daniel Wallach. Daniel is my student, and he'll be graduating, I think, not this year, but next year. And I recommend him. Okay. You start with a net of projections in a 2 plus 1D abstract quantum system. Abstract quantum spin system, so I'll say what that is in a second. We're going to give some local topological order axioms, which are really inspired by the TQO axioms of Brodie, Hastings, and Mikolakis. Then using these axioms, we're going to get something called a holographic dual 1 plus 1D abstract quantum system, abstract quantum spin system called the boundary algebra. And then we're going to say that the local representation theory of that boundary algebra that's going to remember our both topological orders. So that's the strategy for what we're going to talk about in the rest of today's talk. Okay? That's what's going to go. That's going to happen. Okay. What are the TQO axioms? Topological quantum order axioms. Okay? But yeah, so I think you could just take this one and then be like, this one implies both of those, so it'll tell you okay. So we're going to study abstract quantum spin systems. Okay, so a quantum spin system, I've got a bunch of sites on some lattice, and I assign to every point some kind of qubit, and then I have the local operator algebra there, and I can start taking tensor products of this and look at local operators, etc. This goes a little bit beyond that. I just want some local operator algebra assigned to every local region, and I'm going to use rectangles just because it's easy to talk about rectangles, but it doesn't have to be rectangles. Okay? So the empty set just gets the scalars. If I have an inclusion of two regions, I have an inclusion of operator algebras. Okay, just think about these as the local observables. If I have disjoint regions, then those operators should commute. Now, I'm not saying it's a tensor product decomposition. I'm just saying that those operators commute. Okay? And finally, so everything is inside this A. So all these local algebras live inside some big thing called the quasi-local algebra. That's this A. And we're going to say all our local operators generate this quasi-local algebra. And usually I'm going to assume some kind of translation invariance. Okay? So this is our object of study. It's an abstract quantum spin system. It's called a net of algebras. And so examples, you might have some kind of edge lattice in R2, like the toric code or Kitaev quantum double. And then that would just be a big tensor product of matrix algebras that live in that region. You might have a Levin-Wen model that looks something like this. This is my picture of a Levin-Wen model. So that's a Z2 lattice, that's like a vertex lattice. For me, that's where the degrees of freedom live. They live on vertices for the Levin-Wen. Or I might have something that's not a big tensor product of local algebras, like a fusion categorical spin chain, fusion spin chain. There the input is a fusion category C, and I pick a nice object X in there. And if I have n sites in a line, then I'm going to take end of that object to the nth tensor power. Okay, so put X here, X here, X here, just take the endomorphisms, and that's how I view things with this graphical calculus of fusion categories. So they live right there. So that's what is an abstract quantum spin system or a net of algebras. And on this, so instead of a local Hamiltonian, what we're going to start with is a net of projections. So every local algebra gets a projection. That's it. That's our setup. You have a net of algebras. Every local algebra gets a projection. And the only rule is every time I go to a larger rectangle, I get a smaller projection. Smaller projection. If everything's acting on a Hilbert space, a smaller projection means it projects onto a smaller subspace. So how might you think about this? If you had a frustration-free commuting projector local Hamiltonian, then what you do is just take the projection onto the local ground state space. Yeah? And as you get more terms, right? You get more terms in your Hamiltonian, that you're just multiplying by more local projectors, so you're getting a smaller subspace. You're projecting onto a finer and finer spot. Yes? Okay, so here's your example is toric code down here, where I've got my star terms and my plaquette terms. So I got my rectangle lambda, I just look at the local projectors onto the invariant subspaces for those terms, for the star terms and the plaquette terms. So that's P lambda, formula you hold in your hand. Yeah? Okay, great. No, it's a choice. This is the setup. The setup is net of algebras plus net of projections. That's our setup to play our game today. Okay?
So one for each rectangle.
One for every rectangle, and the only rule is larger regions get smaller projections. Okay? This allows you to take some limit, not in the quasi-local algebra, but in like the double dual von Neumann algebra. We don't do it that way, but that's essentially the whole point of doing that. And that you should think about like this limit projection is like the projection onto the unique ground state in the thermodynamic limit. And that's what nets of algebras let us do. They let us rigorously talk about the thermodynamic limit, right? So Lucas was talking today about these technicalities in thermodynamic limits. Operator algebras is really one of the languages that lets you do it really rigorously. Yeah? Okay. And also, please stop me at any time and ask questions. I know we have like 15 minutes at the end, but I'm happy to answer questions at any time. Okay. Our axioms, LTO1, local topological order 1. There's this notion of what it means for one rectangle to completely surround the other by a certain surrounding constant. So as long as one rectangle is completely surrounded by another by enough space, then here's my axiom. If I take the local operators that are localized in lambda, those local operators, and I compress it by a large enough projection surrounding it, I have to get the scalars times that projection. Okay? This is a generalization of the TQO axioms of Bravia, Hastings, Mikalakis. There, they just look at a finite system, and they compress by, and they're really looking at a commuting projector, frustration-free local Hamiltonian, and they're taking the projection onto the ground state, and they compress by that. This is inherently an error correction property, a topological error correction property. And the idea is that, like, if you think about the errors that might be localized in lambda to your ground state, if you just project back into the ground state using this P delta, I get a scalar times, I'm back in the code subspace, right? P delta is projecting onto that local code subspace. That's the idea. So
this condition will guarantee that the ground state degeneracy is trivial. Is that right?
Yes, so it turns out, and I'm going to put it on a later slide, that this will give you there's a canonical ground state that if in the case of a frustration-free commuting projector local Hamiltonian, you can show that this will give you the unique translation invariant ground state by compression on local parts.
So you were saying in general it's not coincide with that?
Again, this is just, okay. I have a net of algebras with a net of projections. But I don't know that there's any Hamiltonian, right? So what does it mean to be a ground state? For a ground state, I need interactions to talk about what it means to be a ground state. But I get a canonical state, and that state is a pure state. Okay? And it's the unique state that is 1 on all of the nets on my projections in the net from the operator algebra language. Okay? And this property holds for toric code, Kitaev quantum double, Levin-Wen, Walker-Wang in upcoming work, like every nice thing that you know about, nice meaning 2 plus 1D commuting projector model, it satisfies this. Okay? Great. How do you prove it for the toric code? You know, so I'm a mathematician. Let's sketch a proof. Okay. So how does it work? First, Pauli matrices span M2, and my local algebras are just tensor products of M2. So polynomials span the local algebras. So it suffices to consider an operator that's a polynomial. That's step 1. Step 2, polynomials, they either commute or anti-commute. It's just a parity thing. Yeah? Now, if I anti-commute with one of these star plaquette terms that lives in delta, Well, this local projection, it absorbs all these star and plaquette terms because it's projecting onto where they're invariant. So I can just create it from that projector. It goes past the operator x, that gives a negative sign, and then gets reabsorbed. So that tells me that that value has to be 0. And that's a scalar times p delta. So I only have to deal with the case that x commutes with all of them, and then it turns out that if I commute with all the star and plaquette terms supported on delta, then I am a product of star and plaquette terms in lambda, because my operator is coming from lambda. And this is an algorithm, and if you don't want to listen to the rest of my talk, or at any point you get lost, maybe in those intense math slides coming up, try to think about how you would do this. It's just an algorithm, and it's super fun. It's just Pauli matrices, so it's really quite hands-on. The Levin-Wen sketch is, I think, a little more fun. I think this was originally proved for Levin-Wen by work of Zhenghan Wang and his student a few years ago, maybe in 2020. We have a nice proof using skein modules in an approach that I think a theorem that Liang Kong put in one of his papers back in 2014. The idea for Levin-Wen is if you compress your local operator on lambda by p delta, or if you just, what is the projection on the p delta doing in Levin-Wen? It's projecting to this thing called a skein module. So what that means is it's basically all of the, you take your fusion category C and you're looking at all the diagrams you can make by hooking up pictures from C on your manifold. That's what the skein module is. And so now if lambda is completely surrounded by delta, if I compress x by p delta, it's going to commute with this tube algebra action that acts on the boundary of delta, right? Because lambda is smaller than delta, and so you've hooked everything up, and so the tube algebra can just act there. And then finally, the skein module is just an irreducible tube module, and you're irreducible if and only if you have trivial commutant, meaning you're just the scalars. So you had to just be a scalar because you commute with the tube action. So it's really a quite conceptual proof of this, and quite quick.
David?
Yeah.
So I feel like I'm pretty familiar with the Levin-Wen model, but I don't know what this picture, how this relates to it. Can you say a few words about that?
Yeah, so I use a unitary tensor category version of the Levin-Wen model. Not like, yeah. So what does this schematic mean? When I have this is a local Hilbert space. So C is a unitary fusion category here. And usually I just pick I take my object X, which is going to be the direct sum of all the simples in C. And so the Hilbert space that goes here is going to be Hams from x to the tensor 2 to x to the tensor 2. So you might think it's the direct sum of all maps that you could draw from A tensor B to C tensor D. Okay? So it's any map from A tensor B to C tensor D. If you wanted to resolve this into a honeycomb, you could just by taking that 4-valent vertex and stretching it into just 2 trivalent vertices, but for pictures, it's really easy to do. It doesn't really matter what you. But I'm really happy to talk later and go to a board and explain the whole thing. But yeah. Does that help? A little bit. Let's talk after. I'm happy to talk as long as you want, and yeah, convince you this is all good. Okay, so that's local topological order 1. Our contribution is really local topological order 2. So what's happening here? So the idea is that rather than being completely surrounded, let's talk about being maybe weakly surrounded. I'll call it that. The idea is that I'm going to be surrounded sufficiently on 3 sides, again, with enough space on 3 sides, but not on that 4th side. On 4th side, those 2 rectangles are going to agree. Their boundaries are going to overlap in a one-dimensional thing here. So today I've been talking about just 2D lattices, but you could do this in any dimension. It doesn't matter. So it would just be a codimension 1 rectangle when they overlap. Okay, and the idea here is that, the idea here is that when you have this kind of weak surrounding, if I compress the local algebra, again, by the larger projection, I'm not going to get just the complex numbers. The complex numbers would be what happened if you can correct for all the errors, but you can't anymore. What happens is the error terms, they'll coalesce on the boundary now. That's what this means. It means there's some operator algebra, B of I, which really only depends on the boundary and not not on really lambda containing lambda inside delta. It really just depends on that boundary, and as long as lambda goes far enough out and delta goes far enough out surrounding it, again, everything finite regions, you're going to get the same algebra. Okay? So really, this is really a sketchy definition of it, and in the paper, it's LTO2 is really 3 conditions, LTO2, LTO3, and LTO4, that are said rigorously mathematically, but this is just the main idea about what happens, okay? And yes?
Depends on whether the boundary is gapped or gapless.
So there is no gapped boundary
right
happening.
Now, yeah,
There's
yeah.
no gapped or gapless boundary happening.
Right,
this is just a way that rectangles are overlapping in your region.
So you mean this work for all chiral topological
I
orders?
didn't say that. What I've said, this is an axiom.
Yeah.
I'm not saying it always holds, but I'm saying that your space has what's called local topological order. If I have a net of algebras with a net of projections and satisfies LTO1 and LTO2, that's what I call a local topological order. So not everything satisfies this, but Tor code satisfies this, Kitaev quantum double satisfies this, Levin-Wen does, Walker-Wong does. You know,
So it's unclear if a non-chiral topological order will satisfy this or not.
That's right, and I expect that that's actually one of the future directions. Can you do this for chiral things with maybe infinite dimensional algebras instead of finite dimensional algebras? Yeah. So, right, so the B of I is really, it's support on sites near I, maybe not just, you know, so over here, this is like the Tor code or the Kitaev quantum double. It's not exactly the things that are on that boundary. It kind of goes a little bit into it, but not much, okay? So another way to think about it is, I said, when you compress the local operators on all sides by that P delta, you get a canonical state. Here I get a canonical quantum channel instead of a quantum state. And so instead what you're doing is you are forcing all of these local operators into the boundary. Okay, so you have a quantum channel to where the errors coalesce on the boundary. Okay? All right. So for Tor code and the Kitaev quantum double model, you just compute what happens in a very similar way to what we talked about. This B of I is generated by these patch operators that have appeared in some work of Xiaogang Wen and collaborators. And so really, what happens here is I look at the projections onto the one-dimensional spaces here on those edge sites, onto the span of G, and then summands of partial plaquette operators. So basically, what survives in the boundary thing for Tor code and Kitaev quantum double, it's basically pieces of the Hamiltonian that aren't quite in there. They survive because they still commute with the other stuff that's there. So they survive, and then these become there are these error operators that are coalescing on the boundary. And so what happens is that these algebras B of I, if I think about taking inclusions along this one-dimensional, this codimension 1 defect, if you will, it's not a defect, but just codimension 1 slice, what you're going to get is the fusion categorical net associated to this Hilb G fusion category with generator being the group algebra. Okay? So that's effectively what you're getting when you do this one. Now, if you take the smooth boundary, you actually get rep G with this C to the G. And so what this tells is actually that Kitaev quantum double, it's not really like Levin-Wen for one or the other. It's actually like it for both, depending on how you think about it. It's a model for the quantum double. It's in the title, right? So that's how this works for Tor code and Kitaev quantum double. For Levin-Wen, the boundary algebra is a fusion categorical net for C. So this is, and the idea here is just, it has to do with you project to the skein module that makes it look like, you know, part of this fusion category, pictures from the fusion category. And then the idea is that this is like what the skein module looks like, and then it's left multiplication commutes with right multiplication. I have like an action on one side of the rectangle and it commutes with an action on the other side of the rectangle. And that's the main idea about how it works, but you get the fusion categorical net from Levin-Wen. And so yeah, so this time that I've been spending here at KITP, it's been really wonderful. And actually I've been talking a lot with Xu Hang, and this fusion categorical nets are actually going to give us some interesting examples on of nets on the circle. So anyway, thanks for starting that project. It's actually been really cool. Yeah. What's a fusion categorical net? So the picture, is there a little button? Okay, the idea is I have a Z lattice, and I have a fusion category C with some choice of object X. And if I have some consecutive sites, I assign this algebra to those sites. So that's just a net of algebras that it satisfies the axioms of a net of algebras. So that's what we call a fusion categorical net, or a fusion spin chain. Okay. Yeah.
So it's feel the strong hard duality does satisfy the weak approximate high duality.
So this is nets on S1. These are not for cone algebras. I think you're going to ask me something about cone algebras. So this is a different type of, this is like I shouldn't have even put that in there because it was, but yeah. Well, I think I know the question you're asking, but let's talk after. Anything else? Okay, so I'm going to use this word topological holography. So I mean this in the sense of Xiaogang Wen and his collaborators on these papers here. These boundary algebras give a precise mathematical formulation of it, where the boundary algebra, it's this discrete 1 plus 1D net, holographically dual to the bulk theory, this 2 plus 1D theory. And so the idea is that the bulk topological order should be characterized as like these local representations. The official name for it is DHR bimodules of the boundary algebra. So in order to explain any of that, I need a little bit of intense math. This is where the intense math starts. So DHR bimodules are due to Corey Jones, and in essence, the idea was he looked at this DHR, Dapcher-Hogg-Roberts AQFT approach of localizable and transportable endomorphisms of the quasi-local algebra and translated this into what should happen for bimodules. And so that's where these definitions come from. So what's a DHR bimodule? This net of algebras B, it could be any net of algebras, so this definition of a DHR bimodule makes sense for any net of algebras. We're just going to do it for the 1 plus 1D boundary algebra. But the idea is the bimodule can be localized in any large enough region. And what does that mean? It means that I can there's some finite number of elements of n here, such that every m can be written as some bilinear combination of those finite elements. That's what I would call like a finite it's like finitely generated projective is the math term for that. And moreover, those finitely many elements, they commute outside for operators supported outside of that interval any large enough I. Okay, and so if you pick your I can find a nice projective basis that lives in that interval, so to speak, so that it commutes with other things far away, no matter what. That's the idea of DHR bimodule. So this definition, I mean, you can actually build these bimodules quite easily for the fusion categorical nets out of an object in the center. So what you do is you basically, you have this object X and you start taking HOMs, and here's the picture, right? You take X, like n copies of X here, n copies of X here, and this center string, it's in the output, but I'm going to draw it to the side because it makes sense when I start taking inductive limits by adding more strings. But the idea is that if I start taking limits here, if I have something supported over here, it's going to commute because it just goes through the strings, okay? Whereas, and here, these are just finite dimensional spaces, and that's going to give me my finite projective basis, okay? So I can build these DHR bimodules from any object in the center, and Corey's theorem from this 24 paper called DHR bimodules and fusion, I don't know, something like that. It's all about DHR bimodules. DHR bimodules for a 1D net of algebras forms a braided W star tensor category. W star here means von Neumann. And the DHR bimodules for the fusion categorical net, it's Z of C. Okay, so what have we done here? We started with some net of algebras with these projections. We use those to get this boundary algebra. And the boundary algebra gives, I look at its local representation theory to get a braided W star tensor category. And in the case of all the examples, these 2 plus 1D commuting projector models that we know about, we get the right answer for what should be the topological excitations of the bulk. Okay, so really, this affords a topological holography perspective on how to get the bulk order from these boundary error operators. About 5 minutes. Okay. So I said intense math like 2 out of 4. So the reason I put in the next 2 slides is because people keep on asking me about types of von Neumann algebras. So I'm going to talk a little bit about types of von Neumann algebras. Cone von Neumann algebras. Okay. So I think, Liang Kong asked me at the beginning about a state, right? So if you have this complete surrounding property, compressing by the projection for the big region to the small one gives me a number times that projection, and it's really independent of delta just beyond the fact that it completely surrounds it. You can take a bigger delta, it doesn't matter. But I get, it's the unique state that evaluates to 1 on every one of these projections, and that tells you it's a pure state, okay? And when that, I think I said it in words earlier, but from an LTO coming from a translation invariant frustration-free local Hamiltonian, this is the unique translation invariant ground state, okay, from Bradley and Robinson. So when you have this state, what you can do is you can complete your algebra to a Hilbert space using the so-called GNS construction, and I can look at the von Neumann algebra generated by any region. And the von Neumann algebra generated by any region gives me a factor, and when it's a cone, you get a properly infinite von Neumann factor. Factor means maximally non-commutative. And properly infinite means that it could be, there are basically 2 types it could be type 2 or type 3. Okay, so it's got to be a type 2 factor or a type 3 factor. Well, which is it, Dave? Is it type 2 or type 3? And this is what people have been asking me about. And it turns out, so if you're thinking about the AQX, yes, oh, you have a question.
Yeah, I can project my voice pretty well. Hi, why do you need a GNS construction for a discrete model unless you need it for the algebra of just one site? I mean, there are no zero norm states unless you have them for just single sites.
Right, so one thing is, there are lots of things to say about that. So why do I need to take you said, why do I need to?
Why do you need the GNS construction?
Why do I need the GNS construction? Right, so if I actually want to talk about a von Neumann algebra, then I need a state and do the GNS construction if I want a von Neumann algebra. The point is that the limit of those projections, ground state projections, doesn't live in the quasi-local algebra. It doesn't live in the C-star land, it lives in von Neumann land.
Okay, so it's not just the original lattice algebra.
Yeah. The point is that in order to take thermodynamic limits, you have to take limits as these algebras get big, and then I look at that state, look at that algebra in that state, that gives me a Hilbert space, and that's where it's coming from. It's really for the thermodynamic limit.
Okay, that answers my question.
Right, so it could be type 2 or type 3. For 1 plus 1D chiral CFT, if you're doing that via the algebraic quantum field theory approach, you always get type 3 factors. Always. For a conformal net, okay? You're always going to get that for these nets of algebras on the circle. So I thought that these should always also be type 3. They should be type 3. So I had my student Daniel, I said, let's try to prove they're type 3 for these models. And so for 2 weeks, we tried to really prove they were type 3, and we found some papers like, oh, we can use this to show it's type 3. And then Ogata put out a result that's saying there was type 2 for the Kitaev quantum double model. And I was like, wow. That's amazing. That was really surprising. I thought it would be type 3 based on what I knew. And it was very surprising because it actually showed us that the paper we were going to try to use actually is wrong. So we were like, okay, there's an error here, and so we believe Ogata. So let's try to figure out what's happening. So we're like, oh, maybe they're always type 2. Now we're going to show they're always type 2. Well, they're not always type 2 either. And so for the toric code and quantum double, they're type 2. But for Levin-Wen, you get type 2 if and only if this quantum dimension of every object is 1, if every object is invertible. And otherwise it's type 3. And so I gave this talk in the University of Tokyo, summer of, I guess, 23, and they were like, well, what kind of type 3 is it? Because there's type 3 lambda. And then Masaki Izumi basically solved this problem for us. He was like, oh, you should look at this. And then the next day, oh, I have some more pages. And then the next day just sent me the whole proof. Like it was like 2 days after I gave the talk, he just couldn't stop himself. He was so, anyway, it was wonderful. So he has an appendix to this paper that tells us what kind of type 3. And so type 3 is really good for things like embezzlement of entanglement is one of the applications for having a type 3 algebra. And if it's type 3-1, and we know exactly when it's type 3-1, it's called a universal embezzler. So really, we just thought it was surprising from a math perspective, but it's actually got some applications to quantum information, and so I thought that was really cool. Why is it this? Well, you can just calculate, and this is a really fun calculation to calculate the canonical state. The idea on the boundary algebra, you look at this operator, and then you squish it by a big projection to the ground state, and you just do the calculation, and you end up with this formula, and I was like really annoyed at these DAs were just in there, because I'm like, oh, it should be a trace, I should be getting this answer. Why am I not just getting the canonical trace coming from the category? But I had all these numbers around. They're reminiscent really of this Plaquette operator, right? 1 over the global dimension summing up times these quantum dimensions times something. It's really coming from the Plaquette operator. So it's a natural formula. But you can see it's a trace exactly when all of these are 1. Then I just get the trace. And otherwise, you do some von Neumann algebra theory, and you show that this has non-trivial modular automorphism group. And anyway, you just do some technical von Neumann algebras, and it turns out it's type 3. Okay, so future directions, and 1 extra minute. Where can you go with this? Well, in work in progress, we're going to do boundary algebras of the 3 plus 1D Walker-Wong using braided fusion categorical nets. So there, you have a fusion categorical net lives in 1D, but if you have a braiding, you can do something in 2D. So that's pretty fun. And you can do that to characterize the point excitations, and you're going to get the right answer in terms of the Muger center of the braided fusion category that goes into making the Walker-Wong net. You could try to, when I have a student who's trying to connect this to the entanglement bootstrap techniques, which they use strict area law for entanglement entropy, and they did some exciting work where they found like commuting projector parent Hamiltonians, and they were able to actually get that they were missing the whole 6J symbols from their original 2020 article there, and then they did this thing where they did a cut. They did a boundary. They looked at the boundary, and then they're able to find these 6J symbols in the very, I'm like, you looked at the boundary. That's good. And I'm hoping that you can just show that their thing satisfies the LTO axioms, and so that would be a nice connection. I want to connect this to the DHR bimodules to AQFT super selection sectors that Peter Nykins and Ogata have been working out, and that would be a nice thing to do there. As Lian Kong said earlier, I want to adapt this to study chiral 2 plus 1D topological order. That's a big ask, but I expect you can't do it with finite dimensional algebras, and you might have to go to bigger infinite dimensional algebras. But there may be a way to do that, and that's exciting. And what would be cool is to give a model-independent operator algebraic way to get higher modular fusion categories of excitations for higher dimensional things. Okay, so that's where we're thinking of going with all of these types of questions. So thank you for listening. I appreciate it.
Do you have any example which has LTO1 but not LTO2?
That's a great question. I don't know any example that satisfies LTO1 but not LTO2. Great question.
Thanks for the talk. Maybe this is a naive question, but regarding this type classification for fundamental algebras, how essential that we have like lattice model here? So if you do, I think I asked you, but if you do the similar thing for continuum TQFT, say some Charles-Simon theory, and look at the algebra of local observers, would it be sometimes type 2 or is it always type 3?
So I don't know what to, this is I don't know what to do there. But that's a very interesting question. This is our techniques here are really just for lattice. Yeah, thank you. That's a good question though.
Hi. When you said that the quantum double model gives you type 2, was that only for abelian groups or for every finite group?
So it works for every group for the quantum double model. Ogata's proof is for abelian groups, but her proof really works for non-abelian groups. And so I actually had this paper here. We prove it here in this paper that this canonical state is a trace.
So for non-abelian groups.
For non-abelian groups, the Kitaev quantum double model, yes.
Yeah.
Yes.
So then you're saying it's type 2. I would expect that the Kitaev quantum double model and the Levin-1 model would be in the same phase.
Oh, yes.
But it's
So
type 3 for one and type
good
2 for the
question.
other.
Very good question. Yes, fantastic
Okay.
question. The boundary algebra, it's not like it's a thing that's holographically dual to the specific bulk model you've written down. It's not something about it. It's not actually for the topological order. It really has to do with the lattice model itself. It's beyond just the topological order, okay? And it's the representation theory of the boundary is what gives you the topological order of the bulk, but it has to do with the actual model. So let's go back to this slide, this type classification slide. You could have already objected here, okay? So here, it's possible if you take G for non-abelian, as you say, vec G has DC1 for every C. So that's going to give you type 2. But rep G is going to have, not D, is going to have larger dimensional things, and that has type 3 boundary algebras. The type of the boundary algebra, it's not just about the topological order. It's beyond the topological order. And even if you started doing things like even doing these finite depth quantum circuits to go between like Levin-Wen and the Kitaev quantum double, this isn't necessarily going to be preserving the boundary. It's not going to be like a bounded spread thing on the boundary algebra. Okay? The boundary algebra is really about the local error operators in this particular model. That's a really good question. Thank you.
Actually, this is incredible. I didn't realize this. So then if you take, rep G and just CG, and they have the same center. So one is type 2 and one is type 3.
One's type 2 and one's type 3, yeah.
But the type 3 is the cross product of type 2 infinity with R. Should
That's
be
right.
very simple.
That's right, that's right.
Do you know the tensor product is very simple or it's complicated? You don't know.
Sorry, the tensor, the what?
So they give you a type 3, give you also a type 2.
Yes, that's
But
right.
the type 3 is a cross product type 2 infinity cross R.
Yeah, but they're all just hyperfinite factors, and so of course they're going to be. It's going to be just the. It is the type 2 factor. There's a unique hyperfinite type 3-1 factor. There's a unique hyperfinite 2 infinity factor. So it's always the same factor that you're getting. It's just a difference.
It's about the factorization.
Oh yeah. The factorization
about
comes
the
from
factorization.
that comes from the modular automorphism group action, and that actually comes from these dimensions of the. That's tied into the dimensions in the fusion category. But that's always there. That's like the Takasaki duality.
So I have a question. What does the von Neumann algebra approach tell you when you put the string net on a surface with a certain genus, like on a torus? Are you guaranteed that the ground state degeneracy does not grow with the system size and all this, or is that because in the language of tensor networks there's a condition very similar to LTQO, and this is called MPO injectivity, and that is exactly the condition that guarantees that the degeneracy does not grow with the system size.
That's really interesting. I'll have to think about surfaces with genus, because one of the things, if you take this approach is really for things without genus, but you could put genus in like the middle of it, but the idea is somehow like, this is a way of looking at like thermodynamic limit, right? Because you're taking these limits as this boundary algebra is going to infinity. I really have to think about that. That's a really good question, Frank.
Yeah, hi. So we're working with some models defined in higher dimensions. My question is, do you have a canonical way to define the Cohen-von Neumann algebra in higher dimensions? Because that's a problem we are having right now.
Oh, how could you do it in higher dimensions? Yeah, we could talk about how to do that.
Sure.
If you're doing, say, a Walker-Wong type thing, yeah, so you can do it in several ways. It's really depends what you want to use it for, but you could just pick the idea that you think about a cone is like what? You take a circle and you have an arc on the circle.
Right.
That's like the angle of the cone, and then you have an apex. And that tells me what the cone is.
That's my diffusion, right?
Right?
Yeah.
So then you can do a lot of things. Just take a two-sphere, and you could do some kind of convex region on a two-sphere.
Right.
And then pick an apex, and that would give you some kind of cone. You could work that way. If you really wanted to work with some kind of, uniform thing, you could take circles, embedded circles on that two-sphere, and then take an apex, and that would be a cone. But I don't think it doesn't really matter to me so much about the actual shape of the cone for things that we have. But I'd be happy to chat with you about that.
Sure. Yeah.
I will say also, since there's a little time, shameless plug, I'm writing a book with my graduate student and my postdoc Kyle called Unitary Quantum Symmetries Light. And I noticed that my course notes have started getting citations in some physics papers. So I was like, oh, this is awesome. But they're course notes. They're not really permanent. I'll try to make them a little more permanent. So anyway, that'll be out soon in geologic time.
Any more question? Well, if not, actually, let me ask a quick question related to the previous one. Can you go back to the type of algebra slide? So in the case of quantum double, is there a way to pick a different boundary algebra such that it's type 3 in the case when G is non-abelian?
So you want to take it, yeah, so it's very inherent on the model, right? So one of the reasons you can get a type 2 factor from the quantum double model is there's like a regular representation of a group. The group can act on itself. And when you use that regular representation, that's what gives you the nice type 2 algebra. So I could have done something different for my Levin-Wen model. I chose this object X to be the direct sum of all the simples. But that's kind of an arbitrary choice. You just need X to be big enough. Right. And so you could have, in principle, chosen a different object. And then if you choose a different object, that could give you a different type of algebra. So assertion, one just has to check, or exercise maybe, because it's definitely going to work. It'll work. So just in the case where it's rep G, don't take the direct sum over all simples, take the regular object. Take like the group algebra for rep G, or C to the G, right? Functions on the group is the representation. That one will have a type 2 boundary algebra. Okay? And the reason is because really what you want is this idea of a regular object, and that's what goes into this Plaquette operator, right? That's kind of, that is the Plaquette operator. It's like the regular object, 1 over the quantum dimension, dc times c. Now the problem is that doesn't make sense here if you're an arbitrary fusion category. It only makes sense if you're maybe an integral one. So conjecture, if you're an integral fusion category and you pick the regular object, it should be type 2. And if you're not picking the regular thing, if there is no regular thing, you get type 3. But that's good. Type 3 is good.
Right. Any other question? Well, if not, let's thank Dave again.